So this last presentation, the first one, is entitled on determining the optimal lifting law of the walking propulsion device foot on an underwater robot from the bottom, and the presenter will be Liliya Smirnaya.
Now listen.
Yes, we are hearing you, so when you want, you can start.
Excuse me.
Okay.
Good day, dear participants of the conference. My name is Liliya Smirnaya. I am from Volgograd. I am a postgraduate student of the Department of Theoretical Mechanics, Volgograd State Technical University. Let me present a report on the topic on determining the optimal lifting law of the walking propulsion device foot of an underwater robot from the bottom. The use of underwater robots with walking propulsion devices has been studied for a long time. For example, Aqua Robot, underwater robot from Japan, for exploring the depths of the sea, was developed in the robot laboratory at the Port Harbor Research Institute of the Ministry of Transport of Japan for 4 years, 1985 to 1989. A robot performing underwater inspection work instead of drivers and to have good stability, positioning ability, and the ability to negative even seabed. In the next picture, it's a robo-lobster, underwater walking robot designed by the Professor Joseph Ayres. This excuse me, this robot is designed to analyze seawater and to find and destroy underwater mines. And on the 3 picture, it's an underwater robot, Crabster CR200, the world's largest underwater walking robot from the Korea. On the third slide, you can see an example of using the cycle walking propulsion device for underwater robots. At our university, Professor Vadim Viktorovich Chernyshov, together with the Central Design Bureau Titan, developed the underwater robot Mach 1. This robot has 6 legs. On the 4th slide, show variants of solving the problem on transferring foot walking mechanism. A future on the first picture is presented the trajectory of transfer of robot foot. 1 is a profile of the support surface. 2 is an absolute trajectory according to Nikolai Vladimirovich Umnov, and 3 possible trajectory. On the 2 picture is presented design scheme of the robot Autonok, also developed in our university. 1 is the body of the robot, 2 the propulsion device, which is interacting with the support surface. 3 the transferable walking movable propulsion device, and 4 trajectory of the movement the foot of the walking propulsion device. A future of ground-based mobile walking robots is the description of the interaction of the propulsion device with the ground. The phase of the interaction with the supporting surface, in which the traction properties of the propulsion device are realized, is distinguished, and the transport phase, in which the foot of the propulsion device moves in space and taken a new position on the ground. This movement includes lifting of the foot above the ground and moving into a new position to the course direction. For ground-based mobile walking robots, variants of solving the problem of transferring feet walking mechanism are known. For example, a modified feet transfer path is known. Proposed is the absence of sufficient information about the surface profile, or the equation for the optimal raising and lowering end of the foot of an orthogonal propulsion device if such information is available. Moreover, the optimality criteria can be different and additively include indicators differing in their significance, such as, for example, the level of the heat loss in the engines, the force developed by the drivers, the transfer time in general, and the raising and lowering of the foot. A future of walking robots moving along the bottom of a reservoir is the presence of buoyancy forces affecting the forces of interaction of the propulsion device with the ground, a higher force of resistance to movement to the robot as the wall and of the transported mover due to the movement and denser environment. Possible undercurrents that affect a transported propulsion device in an arbitrary direction. Additional resistance force acting on the foot of the mover when it is separated from the bottom during the rise due to the absorption of gases dissolved in water and slow filtration of the liquid in the soil. The latter leads to so-called compression effect, which consists in the fact that the significant force that impedance the shear entering to the propulsion support from the bottom soil. The need to overcome this additional force leads to increased energy records for movement of the robot, and in some cases can lead to a stop, can lead to a fit of the robot and its force impression in the bottom soil. Overcoming the negative consequences of the compression effect can go in different direction, improving the construction of supports, introduction additional mechanism that will the conditions for this effect to occur, as well as constructing such laws for controlling the movement of the support of a walking propulsion device that would provide a minimum of energy for lifting and minimum of forces developed by the drive or the performance indicators, or a comprehensive criterion that taken into account part for all of the possible quality indications. The lifting of the foot can be carried out in accordance with variance laws of the drive of its vertical movement. In this case, the force, power, head loss level, and other characteristics for the lifting process developed by the drive will depend on selected law, and you can find the conditions under which the movement will occur with the best indicators from the point of view of the researcher. The task of the presented research is to determine such a flow of vertical movement of the foot for a given time which ensures a minimum of head loss of drive motor. Head losses are determined by the integral, where nu is the constant of the engine, T is the force developed by the drive lifting the foot on the propulsion device, and tau is the set time. The seventh slide shows the design scheme of the propulsion device impressed in the ground. Bottom soil. A horizontal plate of mass M and area S, transitionality moving along the vertical axis in a liquid medium with a known permeability coefficient K and dynamic viscosity mu is considered as a design scheme for the foot of a walking propulsion device interacted with the bottom soil of a reservoir. On the 8th slide, you can see basic laws used in the mathematical model. The solution to this problem is based on the Henry's law of the concentration of gas in a liquid medium, the law of its expansion of the polytropic process when the foot is lifted, Darcy's law of liquid filtration, and the theorem of the movement of the center of mass of the foot as a solid body at the beginning of the foot separation from the ground. The result is the equation shown on slide 9. The 9th slide shows the basic equation. The peculiarity for this equation consists in a second order differential equation relative to the speed. This is due to taking into account the dynamics of movement of a solid body together with the law of change in the volume of gas in the liquid medium. The solution method is presented on slide 10. To create Euler-Poisson equations, the functional V shall be compared with the functional that characterizes as a parametric condition. When the combined interacted function with the indeterminate factor nu has this form, with respect to which in the Euler-Poisson equation is compared. The low optimal lifting of the working propulsion device are presented in this slide. The next slide shows the results of solving the model problem. The graph shows the dependencies of speed and coordinates at the optimal mode of lifting of the foot to a height L is 0.2 meters. depends on speed. In the picture, you can see two graphs. One is an optimal mode, two is a not optimal mode. An analysis of the results show that the nature of the optimal models of motion differs from the previously obtained laws of motion, and the energy optimal mode by the criterion of heat loss exceeds the non-optimal by the 5%. Let me make conclusions. A method of determining of the optimal from the point of view of minimum heat loss in the lifting drive of the working propulsion device, motion models taking into account the additional force acting on the foot due to the compression effect is proposed. It is shown that due to the optimal control of the moment of the support of the walking mower, it is possible to achieve a reduction in energy losses due to resistance to the forces moving underwater. In the future, it is planned to build a laboratory model for studying in the movement of a walking mower underwater and interaction with bottom soil to verify and adjust the mathematical model proposed in this work. This is a reference on this slide, and thank you for your attention.
Thank you very much for your presentation. So I would like to know if there is any question from the audience. Is there any question regarding this work?